hidden mechanisms of the macrocosm down to the smallest atoms, black holes, zodiac, and atomic structure. The universe and the world around us operate in harmony through the motions of three black holes, KH hole, K hole, and A hole, and the dynamic orbit of our solar system. These motions mirror the movement among the constellations, zodiac, reflecting the intricate design of the cosmos. On an atomic scale, this celestial rhythm introduces the idea of incredibly small, rotating particles within atoms that move with extraordinary speed. These particles follow orbits resembling the celestial pathways of stars, creating a dynamic system that allows atoms to occupy smaller spaces and stages. To understand this intricate mechanism, viewers are encouraged to watch the first segment of this series, which explores the connection between black holes and constellations, enabling a clearer vision of these microscopic universes. 7 layers of creation and the Amini system. To simplify the depiction of creation's 7 stages, the interconnected black holes, KH hole and K hole, and the solar system are grouped within the 6th orbital level of the cosmic framework. Collectively, these celestial bodies form what is named the Amini Solar System. This system excludes the central A-hole black hole and is not included in this group, yet works cohesively to create cosmic particles. These particles, each with slight variations, are situated in the 6 orbital layers, ultimately converging at the base layer, the cradle of existence. Atomic duality, opposing forces in motion. Atoms are visualized as systems where particles move in opposing rotations to create dual spaces around a central nucleus. In one orbit, electrons move in a specific direction, while in the opposite orbit, positrons move counter to the electrons, linked through the nucleus. These movements generate matter and antimatter on opposing sides of the nucleus, forming a balanced system named the Amini home. A single particle, depending on its direction, may alternate between matter and antimatter without altering its essence. This dual rotary motion system also prevents atomic vibrations, stabilizing its structure. Electron and positron orbitals, interconnected layers. Electrons and positrons are located on the 5th floor of the Amini house and can occupy up to 5 orbital layers around the atomic nucleus. The number of orbitals changes dynamically, ranging from 1 to 5, depending on the quantity of rotating electrons and positrons. According to the Amini orbital periodic table, additional electrons and positrons can be added to create a 6th orbital layer. This forms unstable elements in the periodic group from 87 to 118. Within the atomic structure, electrons and positrons inhabit the 5th layer of existence, orbiting the central atomic vortex. These interconnected layers define the intricate dynamics of atomic systems, highlighting the balance and instability within higher orbital arrangements. Cosmic and atomic parallels. The structure of atoms mirrors the cosmic design. As scientists name atomic particles and identify their motion, they reveal parallels to celestial systems. The intricate choreography of particles, forces, and orbits demonstrates how the universe maintains harmony at both macroscopic and microscopic levels. Building blocks of particles. Protons and neutrons, once considered fundamental, are composed of smaller particles called quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons have 1 up quark and 2 down quarks. Surrounding these particles are fields of energy that resemble rotating galaxies. These systems also reflect the spin 1/2 of light particles, which align with the magnetic poles of atomic structures. Protons, neutrons, and the balance of matter and antimatter. In our universe, antimatter and matter, particles with positive and negative charges, must always coexist to maintain a state of neutrality. Without this balance, they manifest as positive and negative electric currents flowing through matter. Protons and neutrons, positioned on the orbits of top and bottom quarks, often lack perfect balance in their charges. The particle with a denser photon system charge appears more active, while the weaker particle becomes less detectable. This dynamic determines whether matter or antimatter characteristics dominate in a given orbit. Particles reveal their nature, proton or neutron, based on the strength of their associated positive photon system forces and the clustering of gluons. Neutrons emerge in regions with stronger negative charges, while protons appear in zones with higher positive energy. These contrasting fields always coexist, shifting dominance depending on the balance of forces. Particles reveal their nature, whether proton or neutron, based on the strength of the positive photon forces within their system and the clustering of gluons, which are essentially neutrino particles. Neutrons emerge in regions dominated by stronger negative charges, while protons manifest in areas of higher positive energy. These opposing fields always coexist and shift dominance depending on the balance of forces. In this way, matter presents itself as one of these two interconnected energy forms, proton or neutron. When the orbital dynamics of protons and neutrons, bound through their central core, achieve equilibrium between their opposing positive and negative forces, the resulting matter is referred to as a neutral proton-neutron particle. This is what we recognize today as the neutron, slightly heavier than the proton and electrically neutral. It is important to note that matter exists in three forms: proton, positive, neutron, negative, and proton-neutron, neutral. As energy exchanges occur through central vortex portals, complete equilibrium between matter and antimatter remains unattainable. Higher orbital layers, especially the 6th and 7th, grow denser with dark forces, blocking photon energy flow and preventing full stabilization. This imbalance underscores the complexity of matter-antimatter interactions and the layered structure of the universe. Interactions of matter and energy. The interaction between protons and neutrons generates electromagnetic fields, with each particle's spin contributing to the balance of positive and negative charges. The two particles bind through the attraction of their charges, creating a vortex-like system where energy flows between them through a central portal. This exchange stabilizes atomic systems, ensuring a consistent number of particles throughout. The duality of particles. Scientists classify particles into two groups, fermions and bosons. Fermions represent matter, including electrons, quarks, and neutrinos. They carry magnetic charges and form the basis of matter and antimatter. Bosons, on the other hand, mediate forces like magnetism and gravity, enabling the interactions between particles. The interaction of fermions and bosons sustains the balance of the universe. Complex quark systems. Quarks, the building blocks of protons and neutrons, form intricate systems of motion. They are categorized by unique properties such as color, charge, and spin, and exist in different types, for example, up, down, strange, and charm quarks. These quarks define the behavior of particles within atomic systems, shaping the interaction between matter and antimatter. The fundamental forces in particles, a simplified perspective. The boson group and its four forces. Within the categorized table of particles, the second group comprises bosons, which mediate the fundamental forces of the universe. These include the gluon, photon, Z boson, and W boson, each playing a distinct role. Gluon, the strongest force carrier, responsible for binding particles together. Gluons act as pure neutral particles, generating gravity-like attraction that holds quarks within protons and neutrons. On a larger scale, these black particles mimic the behavior of black holes, holding entire galaxies together in cosmic harmony. Photon carries electromagnetic forces and facilitates light and energy transfer. It forms a part of the Higgs boson system, interacting with electrons, muons, and tau particles in orbital systems. The nature of neutrinos. Neutrinos are unique in that they possess no electric charge or color charge. They remain unaffected by strong or electromagnetic forces, moving at incredible speeds. Their influence is only felt at extremely close ranges, and their mass is so minuscule that they are weakly affected by gravity, making them exceptionally challenging to detect. Electromagnetic forces and photon systems. Electromagnetic forces, carried by photons, govern the interaction between light particles and the solar system's dynamics. Photons, along with leptons, electrons, muons, and tau particles, form the Higgs boson system. As photons rotate in their orbits without the presence of gluons, their spin states 0, 1, or 2 alter magnetic poles within celestial and atomic systems. These shifts influence planetary rotations and the behavior of subatomic particles. Understanding Higgs bosons and magnetic poles. When the Higgs boson system interacts with neutrinos or gluons, spin variations, 1/2, create magnetic pole shifts. This phenomenon mirrors the strong magnetic fields of cosmic black holes, which influence planetary motion and occasionally lead to catastrophic events on Earth. The interconnected dynamics of charged particles and their orbits demonstrate the intricate balance maintained across scales. Force carriers and their roles. Each force in the universe is mediated by specific particles. Photon, electromagnetic force. Z and W bosons, weak nuclear force, essential in radioactive decay. Gluon, strong nuclear force, binding particles in atomic nuclei. Interactions within quarks and mesons. Quarks within protons and neutrons are held together by strong forces. These interactions, mediated by W and Z bosons, form a vortex-like system that defines particle behavior. When quarks are split, new particles emerge, such as strange quarks housed within mesons. These interactions occur in highly compact regions, emphasizing the delicate structure of matter. Alpha particles and their formation in atomic nuclei. Alpha particles are composed of 2 protons and 2 neutrons, both actively situated on either side of the nucleus's central gravitational point. These particles arrange themselves across 4 orbital layers, collectively forming an alpha particle. Each side of the central vortex houses 4 neutron orbits and 4 proton orbits, representing the balance between matter and antimatter. The presence of proton-neutron clusters in the atomic nucleus can be easily detected through the emission of alpha particles. When tightly bound protons and neutrons in the central vortex of the atomic nucleus are emitted, they form an alpha particle. This emission, often caused by the decay of the nucleus, releases these particles, comprising 2 protons and 2 neutrons, as a cohesive unit. The process illustrates the existence of 4 distinct orbital layers within the nucleus, where these particles are compactly arranged and layered on top of one another. This structured emission is a testament to the intricate organization of particles within atomic nuclei and the role of alpha decay in revealing their internal dynamics. The alpha particle in nuclear decay. Alpha particles, composed of 2 protons and 2 neutrons, are central to nuclear decay processes. When heavy elements like uranium undergo alpha decay, an alpha particle is ejected, leaving behind a lighter nucleus, for example, uranium-238 decaying into thorium-234. This process reveals the layered structure of atomic nuclei, with particles orbiting in distinct shells. As a result, a uranium atom loses 2 protons and 2 neutrons, which are placed in a total of 4 orbital shells. Beta decay and transformations. Beta decay involves the transformation of particles within the nucleus. Beta- decay. A neutron emits an electron and an antineutrino, becoming a proton. Beta plus decay. A proton emits a positron and a neutrino, becoming a neutron. For greater clarity, consider the example of an alpha particle, where 3 neutrons are bound to 1 proton in the atomic nucleus. To establish balance between forces, 1 neutron emits a negative beta particle, an electron, and an antineutrino, which is a neutrino rotating in the opposite material direction. This emission converts the neutron into a proton, achieving equilibrium with 2 protons and 2 neutrons, thereby equalizing the charges across both sides of the material and antimaterial space. In the case of positive beta decay, where 3 protons and 1 neutron are bound together in the alpha particle nucleus, the neutron emits a positron and a neutrino, converting into a proton. This process results in 2 protons and 2 neutrons, achieving charge balance across the 2 sides of the material and antimaterial orbit, rendering the system neutral. These transformations balance forces within the nucleus, maintaining atomic stability. The release of excess energy often follows, taking the form of gamma radiation. Gamma radiation and stability. Gamma rays are emitted when a nucleus in an excited state sheds its excess energy. This often occurs after alpha or beta decay, stabilizing the atom. That is, when the solar photon system loses its 3 particles or planets, starting with electron particles, followed by muon particles, and then tau particles due to alpha radiation, the collapse of the central solar photon begins. At this stage, the radiation is released with an almost zero spin, and due to the extremely small orbital motion of these particles, they become highly dangerous to living beings. The photons released in this process are a testament to the dynamic forces at work within atomic structures. Cosmic reflection and the big picture. The study of atoms and particles reveals the universe's underlying principles. From the smallest particles to the largest galaxies, the same laws govern creation and balance. This harmony invites us to explore the deep connections between the microcosm and macrocosm, unveiling the cosmic design that links everything together.